Hello everyone, I'm Thinking Tree and welcome back to another video for the series. Today I decided to solve a problem from Hong Kong preliminary test. It was number 20 out of 20 problems in the year 2020. And I didn't solve every problems, it just looked really interesting to me, so I decided to solve it. And I think Hong Kong the preliminary test, or I think they call it HKIMO, preliminary test. I think it is similar level as IMO. I didn't solve everything, but I think that's the difficult level. So it's easier than other Olympiad problems. And if you'd like to try this problem on your own, please pause the video and feel free to try. Now, without further ado, let's start this problem. So we need to find the last three digits of the 2020 term of the Fibonacci sequence. So I think there are a few things that we can try. One thing that we can try is just brute forcing and finding the pattern, but I don't think that will work because finding pattern for Fibonacci sequence would be really difficult if we have three digits. So the only choice that we have is use modular arithmetic and then use the explicit formula. I think that's the only way because so usually when we think of Fibonacci numbers or Fibonacci sequence, we can think of the explicit formula for it, or it's brute forcing. But brute forcing, we know it doesn't work because we have three. We need to find the last three digits of 2020 term, and it's too big. So let's try that. First of all, we know that this is the explicit formula. Something is really wrong with my pen. I think I need to change it. Change the tip. Wait, is this right? It's the golden ratio, right? I think, yes, of course, it should be right. I think so. So this is the explicit formula for Fibonacci number. So the 2020 term should be 1 over root 5 times over 2 minus this one. Now let's try and simplify them because we have to find, so let's say that this is congruent to A mod 1000 and we are finding the generalized root for A. This one I think we can, it's like a slight tip where we can split this, and the reason for splitting them is because you know that A8 and 125, they are relatively prime to each other, so knowing these two will result in this one, so it will be quite easier. So using the explicit formula, let's organize this quite a bit so we can factorize them. First we have 1 plus root 5, forgot the parentheses. Wait, is it minus? Yes, it is minus. Actually here I was trying to find a clever way to compute this because we know that they are conjugates of each other and maybe it just looks so pretty, but I think binomial expansion is the best choice, so let's use that. No, I think it's pretty clean though. Times we have 2020 0, and then we have 2020 root 5 0 plus 1 2020 is minus 1, so this one, and so on until equal until we have 1 to the 0 and root 5 to the 2020. And then we need to subtract this one. So we have 0. Wait, something's wrong. Yes, I forgot to close it. And then it's minus, then it should be plus, right? Because minus plus minus plus. Oh yes, so we can utilize. Why am I keep forgetting to close my? Anyways, we can actually find the pattern here. So it's even here, even, so it should end with minus. Now when we compute this, we have times these two cancels out, and every other ones they cancel out. So we have yes, and then we have plus, oh sorry, times 2, because we need to double them. Times 2 does not, times 2 here, yes, plus 3 2020 root 3, and then plus until we have 19, right? Times 1 to the 1 and root 5 to let's simplify this more. We can rewrite this as times, let's distribute them. So we have, wait, what? We have, I will just not write 1 because we don't really need them. Plus root 5 squared plus root 5. Yes, this is what we get. So is there any way to simplify this more? I don't think so. So let's stop from here and try to compute for B and C. That way we can find A, and that will be our answer. So no, actually for B, I think what we can do is find patterns, because the number, like, it's only 1 digit, and I'm pretty sure a repetition will occur if we use. So the first term, actually the first term, the 0 term is 0, the first term is 1, and the second term is 1, and the third one is 2. I'm going to write it in modulo system so that we can find pattern. So it should be 8, but writing the remainder we have 0, because that's what we can do. So you can think of it like this. You can think of it 8 plus 0, and we are finding the pattern for the remainder, so we don't actually have to think about 8 times any integer k. So we don't have to consider the case, so we can simply write this. We have 5, we have 2, 7, 1, 0, 1. Oh, yeah. So we actually found the pattern. It repeats here. It will continue to repeat. So how many terms do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there is a period of 12. Then we know that 2020 is congruent to what mod 12? Let me do that quickly. I don't know. So we have 82, 6, 72. Wait, 100? Oh no. Wait, 7, 8, 8 seems reasonable. 96, so we have 4. So is first one, second one, third, and fourth. So we know that this is true. Yeah, wait, what am I saying? It's 4. Yes, because it is 4, we know that f of 2020 is congruent to the fourth one, which is 3, mod 8, because this was for the modular system of 8. Yeah, so we found b, so we know that b is equal to 3. This does something. And the reason, if you're quite confused why we have 12 and things here, we don't actually have to do this. I just thought this will be more easier. So we found a pattern for modulo of 8, and then we know that the 2020 term should be in the fourth term in each period. That's why we have 4 here. And the fourth term is 3, so that's why we know that b is 3. I hope that is clear. And let's move on to finding c. For c, I don't want to use the same method because it will be 2 digits and it will be really dirty. So let's try and use this one. So we know that f of 2020 is equal to 2 to the power of 19 1 times. I will just rewrite them like quickly. Squared plus dot 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 plus 5. Yes. Now we want to find the c that makes this true. We want to find the generalized solution for c. Now, before doing that, we know that we have denominator, and we don't really like this, so let's move it. So multiplying, we get plus dot dot plus this one is congruent to multiplying them. Like multiplying them is totally fine for modular arithmetic. Is c. Let's use Euler's theorem here. So we know that the greatest common factor of 2 and 125 is equal to 1. Therefore, 125 is congruent to mod 1 mod 125. And then let's calculate this. The Euler's torsion function. It is this one, which is 100. So we know that 2 to the power of 100 is congruent to 1 mod 125. Therefore, 2 to the power of 2019 is congruent to 2 to the power of 19 mod 125. Let's simplify this. So we have 1024 times 500. Wait, what? Do I need to calculate this? Actually, I don't think we need to do that because we can simply do this. That's the beauty of modulo arithmetic, I think. That's 144 times 2 mod 25 congruent to, what is 144 minus 25? It's 19, right? Yes, 19, so times 2 is 38. Yay, we found it. So coming back to this one, coming back to this one right here, this thing is congruent to 38c mod 125. Now we know that we can eliminate few terms here because we have 2, 4. So from 6 we can eliminate all the terms because root 5 to the power of 6 is simply 125. So we can rewrite this as, because our whole point is to find C. 5 squared 4 is congruent to, oh yes, 38C mod 25. Now is times, yes, 120 plus, what is this? Wait, we need to times, oh no, I don't want to calculate this. Plus, wait, what is this? All over 5, 4, 3, 2, 1 times 5 squared congruent to 38C mod 125. Let's simplify this. I think it is quite doable. Wait, you know what? Actually, we know that this one we can change to 20. This one, how should we change it? So we can simplify this one. This one we get 673. Wait, it's actually dirtier than what I thought. This one, right? Now we can change to 9. This one to 20. So we have 100 right here. 2. So we can change to 300. 700. So we should get 200, 500, 200, and then it should be 75, I think. If my calculation is correct, we can change this to 75. I hope it is correct. I don't want to get wrong answer. I need to do the same thing for this one. So we know that, wait, which one did I simplify? This one, right? So 673. 4. Wait, what should we do with this 4? 9. And then 504. So we have 0 times 673 times 1009. We have 504 times 5. We can change this to 9. We can say 17, 4, 20. This one 20. So we have 400 right here. Oh, I forgot about this number right here. We have change this to 100. Oh wait, we have then 300 here. Am I doing this correctly? We should have 100 here. So this 100. So adding them, we know that 20 plus 75 plus 100. I just simplified everything. Is congruent to 38C mod 125. In other words, 38C is congruent to 195, right? Wait, is it 195? Is it 195? 70 mod 25. I hope this is right. I think we can divide everything by 2. We can divide everything by 2, but I don't. Okay, so let's find what is the inverse, like the multiplicative inverse of this. So the reason why why 38 is invertible modulo of 125 is because the greatest common factor of these two numbers is equal to 1. Therefore, let's use Euclidean algorithm to find the multiplicative inverse. So we know that 125 is equal to what? 3 times 38 is 14, we have 11, yay. And then we know that 38 is equal to 11 times 3 plus 7, and we know that 5, sorry. And let me try that again. So we have 3 times 11 plus 5. We have the 11 equals 2 times 5 plus 1 is, so we can stop right here. So going backwards, we know that 1 equals 11 minus 2 times 5, which is equal to, we need to write it in terms of 5. So 11 minus 2 times 38 minus 3 times 11, which simplifies to 7 times 11 minus 2 times 38. We can rewrite 11. So we have 7 times 125 minus 3 times 38 minus 2 times 38, so it's equal to 7 times 125 minus 21, 23. So this thing is equal to 1. For anyone who is curious, please check this with calculator. I didn't check it yet, so I'm not sure if this is right or not. So apparently negative 23 should be the multiplicative inverse, which is 102, right? Mod. I hope this is right. Like, I couldn't calculate this part yet. It's okay. If we make mistake, we can start everything again. How nice. So times 102 is congruent to 70 times 102 mod 125. So we know that C is congruent to, oh my goodness, do we need to calculate this? But we can use the trick again. So 140, which is congruent to 15 mod 125. So therefore C equals 15. We know these two things, so we know that B equals, where is B? Where is B? Where is our B? Oh, B equals 3 and C equals 13. I mean 15. So F of 2020 is congruent to B3 mod 8 is congruent to 15 mod 125. So now it's quite straightforward. Let's say that 2020 is equal to 8k plus 3. Substituting again, we know that 8k plus 3 is congruent to 15 mod 125. 12 mod, oh no, we need to find it again. We need to find our multiplicative. I don't want to use Euclidean. Oh, magic. 512. 8k. 8 is relatively prime to 125, so k is congruent to. I think this is divisible. It's 2 to the power of 9, right? 2 to the power of 3, 2 to the power of 6 is 64. Oh, nice. So we know that k is equal to 125k prime plus 64. Let's substitute it again. So 2020 is equal to 1. Oh, How nice. Prime plus, what is 8 times 64? It's 512, I think. If I make mistake, please let me know. 515. Therefore, f of 2020 is congruent to 515 mod 1000. Therefore, our answer is 515. I think this is right. Yes. So today the video was quite long, I think. There was lots of calculations, but anyhow, if we talk about it, I think this problem was quite quite straightforward. And the reason why I say it's quite straightforward is because there is no other way but to use our explicit formula, I think. And then to split this, I think was a great idea. Binomial expansion, and then finding the pattern, and then using mode. I think this problem is just asking for like the ability to play with numbers in modular arithmetic. So we have 5 kicks so far. Oh, and then this is not really necessary, but it's quite helpful to know, I think. I mean, you can brute force it, but we don't know when it ends, so using Euclidean algorithm. And I think that's about it. This problem was relatively straightforward compared to other problems. And I really loved this problem because who could ever thought that a Fibonacci sequence is related to modular arithmetic? I mean, it's quite straightforward because it's asking for the last 3 digits, but number theory is always fun. Thank you so much for watching this long video, and tomorrow I will be back with another interesting and very fun problem. Then if you have any other questions or comments, please feel free to share them in the comment box below. And if you like the solution in the problem, please don't forget to share it and also like the video. Then see you tomorrow. Bye!